Sophisticated breaches often begin in the most technical artifacts of an organization, the internal support tickets, incident notes, and chat logs that document daily operations. These unstructured artifacts are essentially the digital exhaust of IT workflows. For an attacker, they provide a repository of raw credentials and configuration data that bypassed formal security reviews. Within these documents, a leaked credential is only half the story. To a defender, the string itself is just a variable. To make that string useful, it must be paired with its specific access target, the exact account, database endpoint, or cloud tenant that the credential authorizes. This progression illustrates how an attacker moves from a text string to a functional exploit. By identifying the credential and the surrounding resource context, they can unlock access to cloud storage or internal repositories. This shift in attacker methodology suggests that defending source code is only one part of a security strategy. Responders must also account for the technical context buried in an organization's internal communications. This outlines the standard response to a credential leak, moving from discovery to containment. The process frequently stalls at step 3. Once detected, a human responder must manually parse the surrounding document to identify the specific access context it belongs to. Because unstructured data lacks a predictable format, this identification is a manual, high-latency task. Responders constantly find themselves reading through pages of dense logs just to determine which system is actually at risk. An alert that lacks the specific resource context forces a responder to investigate from scratch, delaying the mitigation of a live threat. Efficient incident response requires more than just better detection of hidden strings. It requires a system that can autonomously map the relationship between a credential and its target. Traditional scanning tools, like Trufflehog, rely on regular expressions and entropy checks. They are designed to lock onto specific, deterministic string patterns. These tools are highly effective when analyzing well-formatted code commits, where credentials follow predictable prefixes or lengths. But human communication, like the support emails analyzed in the SSA research, breaks these formatting assumptions. Human language is naturally fragmented and nonlinear. When a regex scanner evaluates a request to rotate an Azure storage key, it can successfully isolate the token string itself. However, it often fails to connect that token to the blob endpoint mentioned sentences earlier. Without contextual awareness, the scanner ignores the most critical evidence. This lack of context is why deterministic pattern matching achieves a recall rate of only 27% when applied to messy, unstructured human communications. A large language model offers a solution. Unlike regex, an LLM can read emails contextually, as shown in this single-agent workflow. In a single pass, the model can identify a storage account key and associate it with related URLs that resemble sensitive data but are benign. When a single agent encounters a dense log with multiple distractors and fragmented strings, its reasoning capability is put to the test. Under these conditions, a single model pass can fail by pairing a valid secret with the wrong resource endpoint or flagging harmless test strings as real credentials. Forcing one model to simultaneously detect candidates and infer logical relationships often leads to these errors, limiting the system's reliability for security triage. To address these errors, the secret scanner agent uses a multi-agent architecture, separating the workload. Agent 1, the secret detector, is biased toward high recall, flagging any potential credential. Agent 2, the verification agent, acts as a skeptic, checking findings against the original document. If the detector flags a session UUID, the verification agent can cross-reference it with the context and reject it as a non-credential distractor. This loop also allows the verification agent to correct mismatches, ensuring the credential is tied to the correct endpoint by re-examining the surrounding sentences. This adversarial review process increases resource extraction precision by 16 percentage points compared to the single-agent variant. Validating security tools requires a significant volume of breach data, but sharing real credentials is often a risk in itself. The researchers used a synthetic data generation pipeline to create safe, realistic testing environments. Utilizing the self-reflection loop seen here, a generator and a critic agent work together to produce realistic, benign IT support emails. Once the base document is created, the pipeline injects synthetic, non-functional secrets and their corresponding target resources into the text. These self-reflecting loops allow for the creation of rigorous, high-fidelity benchmarks without the risk of exposing real organizational data. To test the system's limits, 13 security experts were tasked with extracting credential resource pairs from 45 unstructured documents and were benchmarked against the multi-agent SSA. Humans reached 83% precision, but parsing dense logs dropped recall to 51%, taking 71 seconds per document. The secret scanner agent surpassed 97% precision and 99% recall, completing it in under 15 seconds. In incident response, a 51% human recall rate is a massive risk. Missing half of the exposed credentials leaves critical systems wide open. These results indicate that when dealing with high-volume, unstructured text, automated reasoning achieves a level of completeness human analysts struggle to maintain. The secret scanner agent is not a replacement for security experts. Extracting a credential and its context is simply the preparation for the actual work of defense. Acting as a high-speed triage layer, SSA allows security teams to move directly from leak discovery to active remediation. By linking a secret to its specific resource, the system removes the need for manual investigation. This automation allows analysts to focus on higher-order tasks like rotation orchestration, assessing the impact, and hunting for active exploitation. By delegating context extraction to a multi-agent architecture, security engineers can focus their attention where it is most effective, on the response itself.